Hello, today we'll be discussing and dissecting the Structures 1 project on the Spaghetti Bridge. Before we begin constructing our Spaghetti Bridge, we had to investigate what type of bridge we wanted to build. We had several choices as seen in the diagram on the screen. The 5 choices were beam, truss, cantilever, arc, suspension, and cable stay. We had to take into consideration that spaghetti had strong tensile strength but weak in compression. Therefore, we had to keep our compression members as short as possible. Through this, we came to the conclusion that it was best we built a Warren Truss bridge, one of the simpler bridge designs, yet if built properly, will be able to hold heavy loads. The first bridge we attempted was purposefully designed as a trial and error so that our second bridge could be designed stronger and more effective. The bridge had a total length of 370mm and a width of 60mm. It weighed 154 grams and held a total of 5 kilograms. Before construction began, we used an online software called JF Matrix to determine some of the forces that some of the members would experience. One strand of spaghetti had an average sectional area of 1mm squared. The maximum force calculated that a single strand of spaghetti can withstand is approximately 4.5 kilograms. Therefore, we used a point load of 40 newtons. We could then try to determine the approximate total load that this bridge could withstand. JF Matrix was also useful in that it was able to tell us the predicted displacement of the bridge and show us where the weak points were located. This was vital as it indicated where the bridge would most likely fail. We began constructing the bridge by first cutting all the individual strands of spaghetti to its required length. From this point, we glued smaller members of spaghetti together to form larger members, as they would be able to hold larger loads. Furthermore, once all of the members were glued together and had dried, we began gluing the trusses together. The next step was to glue trusses together and create the base. We chose to use 10 small lengths of spaghetti to connect the trusses at the bottom of the base. At the top, we chose to use 5 small lengths of spaghetti as it would not be responsible for carrying as much of the load. Once the construction of Bridge 1 was completed, we then had to test the bridge. We tested the bridge using the device supplied. To be able to test it, we had to sit the plate on the base of the bridge. We then slowly turned the loading wheel to increase the force that was being applied to the bridge. Once the bridge reached its maximum carrying load, it then failed and we recorded the weight it held. The weight was 5 kilos, which converts to 45 newtons and 0.05 kilonewtons. Once we had completed our test bridge, it was then time to move on to our second and final bridge. We knew we had to move on from the Warren Truss as it wasn't strong enough and wasn't able to hold the same amount of force as that of a Howe truss bridge. The bridge had a total length of 400mm and a width of 80mm. It weighed 189 grams and held a total of 15 kilograms of force. Yet again, we used the program JF Matrix on our second bridge as we found it was reliable and accurate and gave us a great idea on what to expect. JF Matrix was used to predict the forces that inside members of the trusses would experience and also the displacement of the bridge. After further analyzation of the bridge, we discovered that this bridge was much stronger than our original bridge. The displacement also differed as it showed the bridge was much more stable and supported. After calculations were made, we had to then begin the process of construction. The construction process was very similar to the first bridge. We began by cutting all the individual strands of spaghetti to its required length. From this point, we glued smaller members of spaghetti together to form larger members as they would be able to hold larger loads. Furthermore, once all the members were glued together and had dried, we began gluing the trusses together. The next step was to glue the trusses together and create the base. This time we decided to add more members to the top and base of the bridge to provide more strength and stability, as the first bridge buckled at the top and the bottom. This time around, when testing the bridge, we had to do so in a tutorial lesson. This gave us the opportunity to test our bridge against others in the class. The same method applied. We tested the bridge using the device supplied. We had to sit the plate on the base of the bridge. We then slowly turned the loading wheel to increase the force that was being applied to the bridge. Once the bridge reached its maximum carrying load, it then failed, and we then recorded the weight held. This time, the total load that our second bridge was able to withstand was 15 kilos. This converts to 147 newtons and 0.15 kilonewtons. These results were expected as the JF Matrix program predicted that the bridge would buckle from the middle. When reflecting back on the performances of the bridges 1 and 2, it was clear to see that big changes were made between the first bridge and the second bridge. The second bridge was able to hold 3 times the amount of the load from the first, whilst only adding roughly 30 grams to it. As we were able to make such big improvements, it has shown that the construction of our bridge was a huge success. Not only was our second bridge able to hold more force, but in doing this we further improved our knowledge on the technical aspects of structures and forces in the process. Overall, this assessment was a huge success as it has enabled us to expand our knowledge in the area of forces and structures.